Hey friends, it's Ben. My hair is pretty bad, so I'm going to put on a hat. This is a video for the vector calculus class, and um, I'm putting this together on the 7th of February, but this is for the 10th of February because, as I've mentioned to y'all, I'm going to be away and I'm leaving this video for you. So, um, bear with me as we go along here because I'm going to be jumping between screens a little bit as I try to prepare things, um, you know, where they would work out as best as I could. And at one point, maybe a couple of points, I decided that I would try to use some software to take care of things. So let's go ahead here and start with that share screen. And I will pop the iPad on there because we're talking about Green's theorem. I borrowed liberally from Wikipedia in putting this presentation together. And so here you'll see the actual statement from Wikipedia of Green's theorem, or at least the equation part of Green's theorem. And this is actually their diagram as well. Okay, so the basic notion for Green's theorem is that you have a curve which forms the boundary of some region. The region doesn't have to look like this. It doesn't even have to be a single piece, but we do need to have certain characteristics about it that are complicated. I'm going to simply say that we're going to look at the case for having a simply connected region here. And then the curve that's along the edge of it is the boundary. And we are by default assuming that we're going around the boundary in a counterclockwise manner. Okay. And so we're saying that if you've got one of these line integrals of a vector field and you calculate then the m sub x and the L sub y, so taking the derivative with respect to x of the thing with the y and the derivative with respect to y of the thing that goes with the x, and subtract there, that you're going to have a double integral that gives you the same result as you would get with a line integral. So a question you might ask is, what's this mean? Why did somebody think of this? Now, I don't know for certain, but I spent some time thinking about this. Notice this term here. If instead of saying minus, you said something about the equality between those, that's the test for conservative vector field when you're talking about two-dimensional stuff, right? So I suspect maybe somebody made the observation that with conservative vector fields, that this quantity here, no matter where you would integrate across, you end up getting 0. And this here, anytime that you've got a closed loop, that you're getting 0 out of it. And they probably did some investigation to figure out what's going on. When I took a look online to see what other teachers refer to in this, they make reference to this integral along the edge being the macro circulation for the field, and then thinking about all the points in between and the micro circulation in there, and this being somehow a net circulation. I don't know how much I follow that, but that seems logically consistent with this idea of somebody linking those two things up. Maybe. Okay. So we are going to look at reason why this turns out to be true. And then we're also going to talk about what you apply it for. Okay. So reasons why first, and then the applications. So with our goal of how we're going to go about this, we're going to take the part that has the LDX and the part that has the MDY and show that you get a certain double integral with that. Okay. So that's where we're heading. And in fact, what we're going to end up doing is just the first one and then sort of shrugging and saying, well, the second one ought to work kind of similarly. Sorry if that's a little bit lame, but here, as you'll notice, let's see if I can make it resize real quick. This is that diagram from before. So just keep track on this that the C1 and the C3 are the top and bottom curves, and the C2 and the C4 are the left and right curves. Okay. I'm just going to shove that over here in the corner. And so here, if we talk about just the L portion, the L portion here, if you go ahead and talk about what it means to do a line integral, then we want to talk about going along C1 here. And that line integral would be an integral from A to B of the L with X put in for the X and whatever the function is on the bottom. So we called it G1 here of X. So that would be, just an integral. And the integral here for C3 of L of XY, well, C3 is the top, but notice that it's going backwards. So that would be the negative of integrating in the reverse direction for the C3, the L of XY. And that would be negative integral from A to B, because it's A and B here, of X, L of X, and G2 of X. So the line integrals that you got for this top and bottom part here are going to be really just what you have from substituting some things in. But then notice that on the C4 and the C2, those are vertical lines. That means that x's don't change, the x doesn't change. And because the x doesn't change, the dx representing a change in x is going to be 0. And that means that these integrals for C4 and C2 are actually going to be 0 every time. Okay. So what this does, or what this connects up with, is if we do a double integral of the partial of L with respect to y, that is the partial of L with respect to y, integrate it dy from G1 to G2. And then when you integrate it from G1 to G2, because we're integrating with respect to y, that means that the derivative goes away and we just have L of G2 minus L of G1, which is the first one minus the second one. And then when you say something about the zeros in here, you can throw them in. And so that tells us that the integral of the partial of L with respect to y dA is going to, the double integral of that is going to be equal to the integral around the boundary there in that counterclockwise direction. Okay. So something similar can be worked out for the M's as opposed to the L's, but it's going to be the same kind of idea. Okay. So we are going to use Green's theorem here. And the thing that we're going to see is that Green's theorem, often you will have an integral one direction or the other. Either it's a double integral that you can trade in for a line integral that's simpler, or you have a line integral that's super complicated, but when you calculate that, that whatever it was, the m sub x minus L sub y, that you end up getting something that's a lot easier, okay? So in this particular case, we've got an illustration about finding areas. Now, as you'll recall, to get an area of a region, you just need to take and integrate 1 dA. Well, if you need to integrate 1 times dA, then you just need to take and integrate around the boundary of the region in the counterclockwise direction, of course, something so that when you calculate the those partials like that, that you end up getting 1. Well, you can do this with x dy, or you could do it with minus y dx. I think your textbook will go the kind of cockeyed direction of having 1/2 y dx minus 1/2 x dy or something like that. And that just seems like that's adding complications here. We are just going to go ahead and do this. And we'll just have to think about that x is going to need to be a cosine t, with the y being b sine t. We talked about parameterizing before, so y'all ought to be able to see what's going on with that. And that means that our dx is going to be minus a sine t dt, and our dy is going to be b cosine t dt. And of course, we're going to be talking about our t going 0 to 2 pi, right? So in doing the integral around the boundary of x dy, that's going to be an integral 0 to 2 pi. The x is simply a cosine t, and the dy is simply b cosine t dt. And that means we have ab integral 0 to 2 pi cosine squared t dt. You all know my story about Don teaching me how to do that. So that ends up having an area of pi. So it turns out that our formula for finding the area of an ellipse is going to be AB times pi. So, yay. All right, our next one here is going to be a similar deal, but it says sketch and find the area enclosed by R equals this. Now, I don't know about you, but I don't immediately know what that looks like. So I am going to go over to my good friend GeoGebra and share screen on that. Let's see, is that GeoGebra? Yeah, that's it. Okay, and what was it? Sine t, cosine t, and it's going to be that figure 8 kind of lemniscate there. Now, the automatic thing that came up from my telling it to do the curve sine times cosine comma sine, it automatically went from 0 to 2 pi because it just knew that. If I say, let's change that to 0 to pi, y'all can see that we're going to actually get just the upper loop there for that, okay? So we've got it already parameterized for us. Where did it go? Yeah, there it is. We've got it already parameterized for us, and we're going to go set that up. I have the feeling with those sines and cosines that we're going to see the same kind of integral come out of that. So let's go ahead and do this. So our x is sine t cosine t, and our y is sine t. We need to figure out the dy. We don't actually have to find the dx. which I totally did last time for no good reason. So we're going to get a cosine t dt. We're doing an integral around this boundary. So boundary of the region of x dy. And that'll be an integral 0 to pi, not 2 pi this time, but integral 0 to pi. And the x is sine t cosine t. And the y is the cosine t dt. Oh, okay. So it's not exactly the same thing as last time, right? Integral 0 to pi, and I'm going to write a cosine squared t times a sine t dt. Now, I want to do a u sub for this with letting my u be cosine t. That says du is minus sine t dt. And so that means when we want to integrate this, we'll have a u squared and a minus du. And when the t is equal to 0, our u will end up being 1. And when the t is equal to pi, our u will end up being minus 1. So that's minus integral minus 1 to 1 u du. I think Nadia pointed out the other day that we ought to go ahead and try to have those in the right order, right? But then I end up with minus, and I hope this doesn't turn out. Wrote the wrong thing there. Minus, not 1/2, but minus 1/3 u cubed from the minus 1 to 1. So I end up with a minus, well, this is bothering me, a minus 1/3 minus a negative 1/3, which I ended up with a 0 area. That's not right. What did I do wrong in this? So my u is, I gotta tell you, I'm not quite spotting it. But let's take a step aside. So I mentioned that I've got my old friend GeoGebra up here beside me. So let's just get GeoGebra to do that integral for us. So we said it was integral period. Okay, why does it? So integral function variable start x and start y. Okay, it's going to insist that I use x's, which whatever, right? But we're going to have sine of x, cosine of x, and then another cosine of x. And the x's go 0 to pi. We hit enter, and we should be getting 2/3. So somewhere I dropped a minus sign on this, but we should be getting 2/3 out of it. So I will put that on the iPad, and I will fix that before I actually let y'all have the final notes of it. Okay, sorry. And I frankly am not going to go back and edit this and fix it. So let's share screen again. And all right, so the next one here is going the other direction. Here we've got water is flowing from a spring located at 0, 0. The velocity of the water is given by v of xy. I don't know that this is realistic at all, but just the notion is that if you take a look at what will happen with this velocity function, as you get farther out in the x and y direction, it will have things that are flowing faster out that way. And in general, it will give you flows going out from the origin. Okay. So the question itself asks us to use Green's theorem to find the amount of water per second flowing over the rectangle here. And so that means that we're thinking about a region plane with it going -1 to 1 and -2. Okay, so -2 to +3. So that's going to be my rough idea of it, like so. And I'm going to grab it here and just move it around. And I'm just gonna ask you to believe me on this. All right. So with regard to the integral going around here, then and we're thinking about the flow that's going across that. Now we're going to swap that over, have the integral around the boundary of the region of this v vector dot dr vector, and we're going to turn it into a double integral across the region. And we will have to think about these as, what do we call them? L and M. And I hope you all have a better memory than I do. I'm having to peek back here and saying, okay, we need to do M sub x and then minus L sub y. So M sub x minus L sub y dA. And so we will have our double integral. We'll go ahead and set it up here in a second. But the M is going to be this x plus 3y. And the partial derivative of that with respect to the x is going to be just 1. And then the L right here, and the partial with respect to y of that is going to be 1. And then we can talk about dy dx. At this point, you've spotted that we don't need to actually do anything because we're integrating 0. But if I'm going ahead and saying the y's, those go from -2 to 3, and the x's go -1 to 1. And so double integral across any region of 0 is just going to give us 0. And what that tells us is that the net flow across this region is going to be 0. In other words, the flow into the region and the flow out of the region end up balancing. Okay, so that's an application there. I don't know how practical it is, of course. Okay, so this next one here is going to be a little weird, because what I want you to do on this is to look through this calculation and see what comes up. All right. So first of all, this says to us to calculate the integral of FDR for this region, and I forgot to put a little circle on there. So let me put a little circle on there to make sure it's the right thing. So we've got this circle of radius r centered at the origin. And so we're going to parameterize it in the usual way and stuff. But let's go ahead and apply Green's theorem to this. So we've got our m and our n, and I scooted them off sideways a little bit there. We've got our m and our n, and we can go ahead and calculate the m sub y. And when we do that, I went ahead and just thought about it as minus y times this stuff to the -1 power, because I hate the quotient rule. And so I said -1 times this stuff to the -1 power. and then minus y times -1, this stuff to the -2 power, and then times 2y. And then to get least common denominators, I'll have to multiply the -1 by x squared plus y squared. And up here on top, we will end up with a y squared minus x squared. Okay. And similarly, when we figure out n sub x, we'll also get y squared minus x squared, which means when we get this n sub x minus m sub y, we'll end up with a 0, right? And as a matter of fact, because of the fact that this is testing things, or this is the same quantity that you look at to test whether or not a function is conservative. Keval may have already spotted the whole idea of getting a potential function out of this and said, oh, okay, so your integral around the boundary of that should turn up to be 0 because we've got, a potential function, we've got a conservative vector field. But let's look at actually doing the calculation. All right. So if you want to do this calculation, you would say that your radius is capital R. Okay. And so you would parameterize it with x equals r cosine t and y equals r sine t right there. Get your dx and your dy as needed, right? And then substitute in your parameterization that you've got and your dx dy part here for your dr. And when you take that dot product here in the top, because you've got a minus r sine t being multiplied by a minus r sine t, and similarly an r cosine t the same way, it ends up that the thing you're integrating has an r squared over r squared, and you integrate just plain dt. So the integral we get out of this is going to be 2 pi. But you may recall in the previous page, we didn't get 2 pi, we got 0. So the question is, what's going on? Is Green's theorem not true? And I want you all to look carefully at this and think about it for a second, right? What's going on here? And if you want to pause for a second and see if you spot it, that'd be a good idea. But after you come back, you can take a look at the actual statement of Green's theorem in your textbook. And do I have a copy of the textbook on here? I do, but it's a little hard to find. So hang on just a second. And this is one of those things where I did not think it through. And okay, I've got a copy of the textbook on here, but it's doing weird things. Let me find what we need to see. And if I was smart, I would have it doesn't say it. Okay, so let me go ahead and share with y'all, but it is a little bit disappointing in that I thought that the statement in the textbook would point this up. It looks like it doesn't. Okay, here is your statement of Green's theorem there. Okay, and it says let D be a domain whose boundary, and they use that funny looking partial derivative symbol before the D to say boundary of D, is a simple closed curve oriented counterclockwise, okay? And then you get this to be true. Now, here is the thing that it's not saying. And my pointer, okay, undo that. My pointer on that is this bit here. In order to say this, you need to have a function that is integrable on that domain. That means it needs to be continuous on that domain. And the function we're actually looking at has a place there at 0, 0 where it's not continuous. And the thing that's happening is that it's not continuous in a fairly bad way. Let's see. Hi, Steph. Did you get the message where I said I was recording a video and wouldn't answer the phone? No. Okay, let me call you back in a minute. Yes, I know. Let me call you back in a minute. Bye. Bye. Okay, so anyway, the thing to notice here is that the M and the N that we're talking about here, because they are discontinuous at 0, 0, and the order of how it's going to 0 is larger than the order of how the denominator goes to 0, it gets there faster, and we're just ending up with a function that where Green's theorem doesn't actually apply. Okay. All right. So is this the last one here? Yeah, this is the last one. Here we're talking about the folium of Descartes. And the folium of Descartes is parameterized in a way that we've given there. Why is my, okay. So if we're wanting to see what that looks like, then I'm going to stop sharing there, share screen, and go back to my GeoGebra and find, where did I put the folium? There. I have to zoom in a little bit so that you can see it. So the folium of Descartes looks roughly like that, okay? And so we're going to want to deal with the parameterization, which is on your paper. And I'm going to come over here and notice that we are going to need to deal with x dy in order to find that area. That means I'm going to have to take the derivative of the y portion. And so what I did was to just take the 3t squared divided by 1 plus t cubed, derivative with respect to t. And I end up with a result out of that that is negative 3t to the 4th plus 6t. And then I went ahead and took that times the x here, and I get a pretty messy looking function out of it. And now I'm supposed to integrate that function. Yay! So I started trying to integrate that function by hand, and when I did, it was just very messy. So I came back here to GeoGebra and said, hey, could you integrate that for me? And I should first of all tell you that when I went ahead and said, integrate that for me, it didn't. It just said, no, that, oh, actually, no, it wasn't there that I did that. Let me show you more. I'm going to share screen to get over to here. I went to Symbolab and told it, here's that thing I need to integrate. And it told me, nope, we do not support those steps in this problem. And I was like, I don't want to do this one by hand though. So I ended up going back to GeoGebra for it. So share screen for GeoGebra. And I also couldn't get GeoGebra to do it. But what I could get GeoGebra to do was to integrate it for numerically. So I told it to integrate it 0 to 1. It said, sure, I can do that. Except where did it go? Yep. And then I said, well, since I need to go from 0 to infinity, 10, that's close to infinity, right? And it got 1.5029 something. I said, okay, 100, that's closer to infinity, right? It said 1.5. And then I said, oh, okay, 1,000, that's really close to infinity. And it seems to be saying to me that, yeah, 100's close enough to infinity. Numerically, it's not changing anymore. It's getting an integral out of it of 1.5. So that's what we've got there. So we're again doing an area by making reference to that integral of x dy and going from there. I'm going to let it go at that because apparently my wife wants me to come home now. Imagine that. All right. I will see you all later. Let me know if you run into any problems with stuff. All right. Bye.